In mathematics and in computer science, we often look for things like patterns. And once we observe patterns, whether those be numerical or logical, we try to make some inferences about that. And so, we might observe that we start adding together two numbers and we find out that, it appears that every time I add two even integers together, I seem to get an output of an even integer as well. So when I do 2 plus 2, I get 4. Oh, look, 4 is even. 4 plus 2, well, that's 6, and that's an even number. If I do 2 plus 8, that's 10. That's also an even number. Well, an even number is any multiple of 2 or any number that you can divide by 2 and end up with another integer. So 10 is 5 times 2, 4 is 2 times 2, 6 is 3 times 2. And this doesn't stop at these numbers. 14 plus 12 is 26, and that's an even number. And so we might be tempted to say, oh, the sum of any two even numbers is always even. And that's where our logic and our intuition have a little bit of a disconnect, because it's inadequate to say, well, here's the pattern. Look at the pattern. It must always hold true. We need to provide some sort of fabric without any holes in it that basically makes our logic foolproof and completely enclosed and sealed. So another claim, a person might have is that you can divide any two integers that you want. So for example, if you take 2 divided by 6, that gives you a real number. So the division of any two integers produces a real number. But then what if we forget about the situation where 0 is also an integer and you can't divide 3 by 0? So we've got to be very, very careful when we formulate our logic. Now in mathematics, a lot of statements are stated as implications. So there's some sort of condition. If the following conditions hold, then this result will happen. So in order to prove such a statement as being mathematically true, well, what does P implies Q mean? It means that whenever P happens, Q should also be true. So it suffices, in other words, for P to be true to guarantee that Q is true. And that is the only circumstance under which an if-then statement is true. The method of direct proof starts off assuming the premise, right? Because what we're trying to say here is if the premise is indeed true. So assume it is, and then show that the result Q follows. We often start off such a proof with suppose P is true. So we then have a series of logical steps that allow us to end with the conclusion. So there's suppose P is true, whatever that statement may be. Then you get to operate with that statement and do a bunch of logical steps, whether that is algebra or making some observations that are true. And then hopefully walking yourself to the conclusion Q. So it's as if I start over here on a path, right? And inch by inch, I sort of keep going and keep going and keep going and say, hey, look, I can always get to Q as long as P is true. And then eventually, once you get down here, you end up with the statement that you were trying to prove. And that's exactly what a direct proof is. So we get to use our propositional logic. We're not going to use truth tables. We've already used them to develop equivalencies. So sometimes when a direct proof is difficult, if you can't start at P and end at Q, there are some other techniques. So here's a real basic one. Here we have prove the proposition if x squared equals 9, then x equals plus or minus 3. You might say in your head, well, I already know that's true. But here we have the statement P. Here we have the statement Q. So the first thing we're going to do is, you usually say something like, here's the proof. So assume P is true, okay? So if P is true, that means assume x squared is equal to 9. So we basically assumed P. Okay, well now I want to somehow be able to conclude that x is plus or minus 3, but I just can't say, look, x is plus or minus 3. I'm going to have some sequence of logical steps that allows me to arrive at what x must be. So when you assume x squared is equal to 9, well then it makes logical sense to say, oh, you know what, that's an algebraic equation. So if I take x squared equals 9, and I take the square root of both sides, and then I take the square root of, or plus or minus the square root of 9, then what I end up with is x is equal to, well, square root of 9 is 3, so x is equal to plus or minus 3. And we've just proven the statement. We basically said therefore, and therefore you can write like this if you'd like. Therefore, whenever x squared is equal to 9, it follows that x equals plus or minus 3. And that is basically how you conduct a proof. Now, this one's algebraic. Not all proofs in mathematics have to be algebraic. Some of them are very difficult and logical ones, but we're just trying to introduce how Boolean logic allows us to observe patterns and then make conclusions about them. So prove the proposition if A and B are both even, then A plus B is also even. So here is what most students want to do, and me included when I was first studying this stuff. They want to say that, well, look, 2 plus 2 is equal to 4, 4 plus 6 is equal to 10. Oh, you want me to do some more? Okay, 10 plus 18 is equal to 28. I'll even give you a big one. 214 plus 106 is equal to 330. So that proves it all right there. But the problem is that only works when A and B are 2 and 2, when A and B are 4 and 6, when A and B are 10 and 18, and when A and B are 214 and 106. So if you only set off to prove it for those 4 pairs of numbers, you've succeeded. However, if you're trying to say that for any even integer A and for any even integer B, the sum of those numbers is also even, this is not going to suffice. So how do we do this? Well, first of all, we have to look at definitions. So what does it mean for a number to be even? Well, by definition of an even number, there is, and you always need to think about this, what is the definition of what I am talking about? What is the strict mathematical definition? So it's nice to say even, but you've got to give me a mathematical definition for it. So even numbers are the set, or E, capital E. This is not a required name of the set, but I'm just using capital E for even here. And the set of all even numbers is numbers of the form 2 times k, where k is some integer. So you can see, for example, if you write any even number, you could always write it as a product of a factor of 2 and something else. Every number is a multiple, every even number is a multiple of 2. So 2 is 2 times 1. And so you can think of k as being equal to 1 here. We can go on and on. We can say 22 is 2 times 11. In this case, k is this number right here. K is 11. So k is just any integer. And we want to remember that the set of integers, in case you've forgotten, is the set of all numbers 0, plus or minus 1, plus or minus 2, etc. So that's how we define even numbers. And so basically we should always be able to factor out a 2 from whatever number we're working with in order to be able to say it's even. So whenever we prove this, we're going to start off with the statement, suppose A and B are both even. And then we're going to say, well, that means A is equal to 2 times K1 for some integer K, K1. B is equal to 2 times some integer. And then we're going to take those two now mathematical quantities and combine them and show that their result is still even. Now, the important thing to note here is k is just any integer. It doesn't really matter what integer k is. It just has to be the case that you can factor out a 2, and then whatever's left over as the other factor is your value of k. All right, that is, all even numbers can be factored into 2 and some other integer k. An odd number is, we'll also define that here because we'll work with those as well. The difference between an even and an odd is a plus or minus 1. Now, it could also be that an odd number is an even minus 1, but for simplicity, we'll just stick with the plus 1 convention. So if you double a number, for example, and then add 1 to it, it's going to be odd. In a similar sense, if I write 5, for instance, well, that's equal to 2 times 2 plus 1. So here is my value of k. If I write 11 as 2 times 2 times 5 plus 1, that gives me 11, and you can see that k is 5 in this case. 99 is equal to, let's see, if I subtract 1 from that, that's 98 divided by 2, so it's 2 times 49 plus 1. And again, k is just some integer, which is going to vary from odd number to odd number. So we don't really focus on the k, we just focus on whether it can be written as 2 times an integer, i.e. even, or 2 times an integer plus 1, i.e. odd. Okay, so now we're prepared, and along with one more fact that we'll need. This is called the closure property of integers under addition and multiplication. So we assume this to be true. It's difficult to prove, but if you add, it's often called an axiom. An axiom is just sort of an assumed truth because something becomes unprovable. If you sum or take the difference of any two integers, you always get another integer. And this is again not proof here, but if we take any two integers like 2 plus 11, we get 13, and that's still an integer. That's still a whole number. If you take negative 7 plus 36, you get 29, which is still an integer. You can take negative 2 minus 7, that's negative 9, that's still an integer, and so on. Same thing holds for multiplication. So if you multiply two integers, 2 times 3, you get another integer. Negative 4 times negative 6 is positive 24, you get another integer. So these are assumed truths. Unfortunately, these are things that you cannot prove because there is no very strict definition for what an integer is. We just say an integer is 0 plus or minus 1 plus or minus 2. So we don't have a really operable definition. Okay, so let's go ahead and prove this statement now, that the sum of any two even integers is going to be an even integer. Now, we didn't say even integers, but when you see the word even, well, by definition, it's going to be an integer because it's the product of two integers, and by the closure property, an even number cannot be a fraction. Okay, so this was the statement we set out to prove, and we again want to point out what our P and Q is because we're going to prove this directly. So P is actually this statement here. A and B are both even. A plus B is also even as the statement Q. Now you notice that statement P is a compound statement. We can define it as P1 and P2, where P1 is the statement A is even, P2 is the statement B is even. So this basically means that if P1 and P2, then Q. A plus B is also even. Now A plus B is one number, so this is not two separate statements. All right, so when we start off with direct proof, we assume the premise is true. So to begin proving this, we're going to assume A and B are both even. Okay, because it's only then that we guarantee that the sum is even. So assume, so as our proof, we'll start off with assume A and B are both even. Okay, well, what does that mean? What does that allow me to say next? And again, all I've done here is assumed P. Well, now I can define those quantities. So that means if A is an even number, then A can be expressed as 2 times some integer. And I'll just call this K subscript A, just so that I know that that's the K value that went with the number A. And then I'll also write B can be written as 2 times KB. That's just a subscript, that's just one letter right there. You could use 2K and 2J if you want. And so now we need to be able to state, well, what are Ka and Kb? Well, Ka and Kb are both integers, so they live in the family of all integers. And where did this step come from? How did we get from assume A and B are both even to A is equal to 2KA and B is equal to 2KB? Well, we usually want to justify our steps, so we'll say this is by definition of an even number. So we haven't done any black magic here at all. It's not like we pulled a rabbit out of our hat. We are using definitions now to logically break down this premise into something that involves equations. And when we have equal signs, then we can actually combine things. So the next thing I want to do is, all right, so how am I going to end up at A plus B is also even? Well, I want to show that when I add A and B, now the conclusion isn't A plus B. The conclusion is that A plus B is even. So there's nothing wrong with me forming A plus B or adding these two quantities together. So this allows me to say that A plus B, which is equal to, well, wait a minute, A is 2 times KA, B is 2 times KB, and this is really just by substitution. That's all we really did here, is we substituted in 2KA for A, and we replaced B with 2KB. Now, in order for me to end up saying that this is an even number, I need to be able to say, I'm going to write this off to the side, we need to show that A plus B is equal to 2 times some integer. Okay, well, I'm pretty close there. I see that both of these numbers have a factor of 2 in them, so I'm going to go ahead and factor out a 2. And if I do that, I'll just have KA plus KB. Okay, so all we did there is just factor. And we already see that it's A plus B equals 2 times some number. Well, the only thing that we need to convince ourselves of at this point is that this is an integer right here. That if I add KA plus KB, I get another integer. Okay, well, by the closure property that we just described, if you add together KA plus KB is an integer. So by the closure of adding together two integers, KA plus KB is another integer. And so let me relabel this I'll just say K equals KA plus KB. It doesn't matter what you call these letters. It could be W for all intents and purposes. But the reason I do this one last step is so that it looks absolutely, irrefutably like an even number. So in this final step, I'll just say, okay, so this was my next step after that. This is my next step was just a statement. And then my final step here is just going to be to say, well, that means A plus B is equal to, and we said that KA plus KB, we'll just call that K, a brand new integer. And so A plus B is equal to 2 times K, which means that A plus B is even. How do I know that? Well, by the definition of an even number, because 2 times some integer is even, and that is equal to A plus B. So if an even number equals A plus B, that means A plus B is an even number. And we could say that this is by definition. It can be written as 2 times an integer, and therefore that's what makes it even. So that concludes our proof, and we've just proven that if A and B are even, then A plus B is even. And that means we're done at this point. So logically speaking, we have to take this step by step, and we have to always try to deconstruct statements into operable mathematical statements. So saying that numbers are even doesn't, I mean, it means something, but the definition of an actual even number in mathematics is twice an integer. Okay, let's go ahead and do one more. We'll say if A is even and B is odd, then A times B is even. So let's start off by just identifying our two statements. And one of those is if A is even and B is odd. Now again, you could break that up into two simpler statements. P1, A is even, conjunction with statement P2, which is that B is odd. But it's not super important because we're not going to be doing any truth table stuff with this. When we assume P is true, we assume both of these things happen. And then this is the conclusion, Q, that A times B is even. So what we're going to do here is we're going to break up A as a definition of an even number, write B as the definition of an odd number, multiply them together and show that we get something that is even, that can be written in the form 2 times some integer. So I'll start off this proof in a very, very similar sense. We'll say, suppose A is even and B is odd. Okay, all we're doing here is we just assumed P. And we want to show that anytime P is true, so is Q. So by definition of an even number, this means A is equal to 2 times, again, use KA, you can use K, J, W, whatever you want. You have to state what they are though. And B can be written as 2 times some integer, which I'll call KB, plus 1. We don't want to call them both just K because they don't have to be the same numbers. They don't have to be one number apart, 1 unit apart. So KA could be 5 and KB could be 256. We have no idea. We're trying to make this as general as possible. Again, you could try some examples, and I encourage you just off to the side to say, well, is this even a true statement? If I multiply something like A and B, and now I look at A times B, and A is even, let's see, 2, B is odd, 3, oh, that's even. 2 times 5, well, that's 10, that's even. Well, wait a minute, that actually looks like I'm taking 2 times some integer, and therefore that's going to be an even number. But let's make this very, very clear and explicit as we go through this logic. Okay, so this is by definition. Oh, wait a minute, but we have to say what Ka and Kb are. These are important details. So Ka and Kb are both some integers. And this is all by definition of even. I'll just leave it like that, you know what I'm saying. And now what I'm going to do is I'm going to multiply them together because I want to show that their product is going to be even. So what am I going to do? Well, I'm going to write A times B is equal to, okay, so I'm going to replace A with 2Ka. I'm going to replace B with 2Kb plus 1. And now you might even actually see at this point that you can just factor out a 2, but let's take this algebra a little bit further so we can see very carefully what happens next. So this is just by substitution. We just plugged in values for A and B. Again, notice that we didn't put in numerical values for Ka and Kb because we don't want to prove by example. Proving by example doesn't work. Examples work sometimes, but not always. So if I distribute this in, I multiply these two terms together, I get 2 times 2 is 4 times Ka times Kb. Distribute that to the plus 1, that's just 1 times 2Ka. And this is just by distributive property. And now, again, I want to show that this is an even number, so I want to ask myself, typically when you're showing something is even, can I factor out a 2 at some point? So I see that both terms, 4Ka, Kb, and 2Ka both have factors of 2 that can come out. Great, well that's 2 times quantity, 2Ka, Kb, plus Ka. And already I'm seeing that A times B is starting to take on the form of an even number. But this stuff in here, this is what concerns us, right? Because that doesn't look like just 2 times some integer, it looks like 2 times some crazy multiplication and addition. But here's the thing. By the closure property, we already have established that if you multiply integers together, you get integers. And so 2 times ka, well, that's 2 times an integer, which is an integer. And an integer times another integer is still an integer. And an integer plus an integer is an integer. Therefore, this is an integer by closure of integers under addition and multiplication. Great, so that means that, so I'll make a statement like this just to make it totally clear. K equals 2ka kb plus ka. You don't have to do this. You could stop at this point and say, well, this is a times b is clearly 2 times some integer, and therefore a times b is even. But I don't know, there's just something pretty about writing it as close to the definition as you can. So a times b equals 2 times this whole mess right here, which we just said was k. And then now that says a times b is even by definition. And so what have we proven? Well, we started off with if a and b are even, if a is even and b is odd, if a is even and b is odd, then a times b is even. And so that establishes how we conduct that proof. So the point among all of this is that we're using clear logical steps where we do one thing at a time. And I realize that some people may do this step differently. Some would observe that you could just factor out a 2 there and not have to distribute all the way through. This is not the exact series of steps that one would need to see every time, but we do need to make sure that our steps follow from one another, because when somebody looks at a proof, they want to be able to say, okay, are there any loopholes in this logic? And the more gaps you keep open, the more that proof will get questioned. We'll look at 2 more types of things. One thing is proving the converse. The converse is not always true, right? But the converse means that if P implies Q is my statement, then the converse of that is Q implies P. This does not always lead to a truth. We learn that with if I am in Paris, then I am in France. That's a true statement. But if I am in France, then I am in Paris is not a true statement. So prove that the converse of problem 1 is true. So problem 1 that we had was if x squared equals 9, then x equals plus or minus 3. And to prove that converse, all we need to do is, once again, start off with our statement and rewrite the converse. So the converse switches the conclusion and the premise, and that would be if x equals plus or minus 3. And let me write it out like this. If x equals 3 or x equals minus 3, because that's what plus or minus means, then x squared equals 9. Now in this case, this statement is going to be true, and it's not terribly difficult to see, because if x is 3, then 3 squared is 9. If x is negative 3, then negative 3 squared is 9. So all we're doing when we're trying to establish whether a converse is true is rearranging our 2 terms, and now our premise becomes Q, and we want to walk ourselves in a series of logical steps to show that this conclusion follows. So suppose, as a proof, suppose x equals 3 or x equals minus 3. And this is going to be a really quick one. In either case, when x is 3, 3 squared is 9. So that's a check. And negative 3 squared is 9. And that's a check. Therefore, Whether x is 3 or x is -3, the square of x will be 9. And so this is no different in logic than our previous two proofs for even and odd numbers. The only difference is here that we're taking a statement that was of the form P then Q, and we basically wanted to say, well, if you flip the conclusion and make that the premise, will that lead to the thing that used to be the premise? And in this case, it does. So because it works both ways, because P implies Q and Q implies P are true statements, we write P if and only if Q, and say P if and only if Q. This is called a biconditional statement. It is true in both circumstances. Now, probably one of my favorite ones when I was going to school was disproving a statement. And disproving something is often easier than proving something is true, because to disprove something, first of all, in Boolean logic, a statement is either always true or it is not always true. So that means if something is not always true, it is false. And that is sometimes a hard pill to swallow, that even if you find just one exception to your rule, that makes that whole statement false. To show something is false, we only need to come up with one example of where the statement fails. This then disproves the truth of the statement. So this is called a counterexample, an example that counters the argument, and show by coming up with a counterexample that the converse of the following statement is false. Excuse me, that the following statement is false, not the converse of. That the following statement is false. So if x is an element of A intersect B, then x is an element of A. Okay, so that means, oh no, I'm sorry, we do want the converse of that. We'll practice the converse of the following statement. So if x is an element of, as inside of the intersection of A and B, you can agree that x is an element of A, right? Because it's inside of A and simultaneously part of B as well. But to prove the converse of this, well, let's think about what the converse would be. Here I have the statement, if P, then Q. So if I want to write the statement Q, then P, that would be if X is an element of A, then X is an element of A and B. And we want to show this is false. Okay, so we just need to find one counterexample. Here we're arguing that for any element that is in some set called A, that it's also in the intersection. So I'm going to try to think of an example. Well, first of all, I can just visualize this and start thinking about what would happen if I had two sets, A and B. And in that set, if I had, or in that universe rather, I had these two sets, A and B. So I'm starting to think about this. What's going through my mind? Well, I know I have A and B, and there's going to be some intersection possibly here. So let's say I have an element inside of A. Is it guaranteed that just because it's inside of A, it's also inside of B? Well, no, because I can pick an element here, or even here, or even here, and all of these points are in, that dot is in A, and it's not in B. So it doesn't necessarily guarantee that X being an element of A is also an element of B simultaneously. All right, so let's actually formulate a more robust, so you could use this argument as long as you use some words, like you could say, as long as the viewer could see this and say, well, here's an example, the elements above in A above are not in B. And so that's the counterexample that we could give. Another counterexample that you might be able to give is a numerical one. So you could say something like, suppose A is equal to the set, we'll say 1, 2, 3, and we'll say B is the set 3, 4, 5. So notice that 1 is an element of A, but 1 is not an element of B. Therefore, not all X in A, not all X in A are also in B. And that's a counterexample. So somebody made the claim, but we just said, nope, your claim is false. I just found an example, or at least one example where your statement is false. And the last thing that we'll look at here is what we call proof by contrapositive. And if you recall, the contrapositive of a statement is the statement starts off with an if-then, because most mathematical statements, most computer science statements are of the if-then form. Sometimes it's hard to prove if P then Q. So it's hard to do this direct proof method that we've been doing where we start on one side and work our way to the other. But we know that the contrapositive of a statement, which is an equivalent statement, is the statement not Q, then not P. Let's just remember why. It's been a couple lessons since we've seen this. So if P, we look at Q and P, false, true, false, true, false, false, true, true. And we know that P implies Q is only false when the premise happens, but the conclusion doesn't. It's true otherwise. Okay, so not Q. So now we're going to show that we get the same column, that you can get an equivalent column for not Q, not implies not P. So not Q is just going to be the negation of false and true and false and true. So it would be true, false, true, false. Not P will be true, true, false, false. And not Q implies not P will be true, but false only when not Q is true, but not P is false, which is here, and it's true otherwise. And we see that this column is logically produces the same value as this column over here. Therefore, if you want to prove the statement P then Q, it's equivalent to proving not Q then not P. So intuitively, consider the statement, if I am in Paris, then I am in France. Isn't it also equivalent to say, if I am not in France, then I am not in Paris? Ah, well, that makes sense. You can't be in Paris if you're not in France. So let's go ahead and take a look at another example here. And again, we'll just deal with the number system. Let's define a rational number. We've seen these before, but a rational number is any number of the form x divided by y, where x and y are both integers and y can't be 0 because then you divide by 0. So these are called rational numbers. They're just ratios of integers. So for instance, 2/3, 0/8, -2, 15ths, -1, -3rds. These are all rational numbers, which we typically use the letter Q to denote that. For quotient, I think is probably the naming convention. And so these are elements of Q. But for example, 3 divided by 0, pi over 4, these are not rational numbers. Why are they not rational numbers? Well, because we cannot have the denominator be 0, and pi is not an integer. It has to be expressed as a ratio of integers. So consider the following argument. If A times B is irrational, then A is irrational or B is irrational. Well, wait a minute, we just defined rational numbers, right? We know what rational numbers, but irrational numbers are simply just not rational. So because it's so much easier to write what a rational number is than what an irrational number is, this is going to be a difficult statement to prove. Here I have the statement P. A times B is irrational. And here I have the statement Q. A is irrational or B is irrational. Okay, so if I look at the negations of these statements and I write them in the reverse direction. So by the way, here'd be the problem. If I wanted to say, assume A times B is irrational, I would have no next step because I don't know what the definition of an irrational number is. We only know the definition of a rational number. So irrational numbers like pi, 3.14159, dot, 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 are non-repeating, non-terminating numbers. So they're very difficult to define. But if I take the negation of something, so not p is the statement that a times b is not irrational. Let me say that first. A times b is not irrational. And what does it mean to say a times b is not irrational? Well, that means that a times b is, if it's not irrational, that means it has to be rational. So this means that, I shouldn't use an arrow, but this means that, i.e., a times b is rational, or is rational, to put more emphasis on that. So that's the first thing we're going to need to do, because we're going to try to prove this by contrapositive, but to write it as contrapositive, we first need the negation of both of those statements. So not Q. Well, Q is a statement A is irrational or B is irrational. So not Q, I'm going to write it like this, is the negation of the statement A is irrational or B is irrational. Now, by De Morgan's law, if I have the negation of a disjunction, that is the same thing as saying it is not the case that A is irrational. So A is rational is the negation of that. And then if under De Morgan's law, the negation of an or is an and B is also rational. So we have to negate that statement. So B is rational. So what we've done here is we've gone from talking about irrational numbers to only working with rational numbers. Everything is now in terms of rational numbers. And if we want to prove if A times B is irrational, then A is irrational or B is irrational, we could instead prove the equivalent statement. Again, equivalent means we'd be proving the same thing, not Q, if not Q, then not P. So let's go ahead and write this. And then at that point, once you rewrite these statements, it's the exact same logical process as what we were doing earlier. Just sometimes we need to massage the statement a little bit to make it more easily provable, or at least quantifiable. So now as a statement, we're saying not Q, then not P. So we'll say if not Q, if A is, I guess I could say if A and B are both rational at this point, because A is rational and B is rational. If A and B are rational, then A times B is rational. Okay, great. So I'm going to assume that A and B are rational. And when I do that, then I can say, oh, well, wait a minute, I could, by definition of a rational number, A is the ratio of two integers, and B is also the ratio of two integers. So this will make it incredibly useful to be able to prove this argument. And let's go ahead and do that, and that'll be our last problem here. All right, so here we go. So the first thing we do is to prove a statement, we start off with the condition or the premise, and so we are going to suppose the premise is true. So suppose A and B are rational. And this is just the statement, well, right now it's the statement not Q, but remember that what we're proving here, not Q, then not P, is equivalent to proving if P, then Q. So suppose A and B are rational. Okay, well, wait a minute. Let me think about that. If A and B are rational, that means A is going to be the ratio of two integers, which I'll call XA and YA. And then B is going to be the ratio of two numbers, XB and YB. This just helps me keep track of where the X's came from. And then wait a minute, what are XA, YA, XB, and YB? Well, XA, XB, YA, and YB are all integers based on the definition of a rational number, and also the denominators can't be zero. So YA and YB, whoops, YB are not equal to zero. And this is just the definition of rational number. Great, okay, so now that I have these nice solid definitions, I can go ahead and prove this statement. So let's see, the next step that I'm going to take here is, well, I want to multiply these two numbers together. So if I multiply these two numbers together, I will get, let's see, A times B. And I want to show that the product of these two numbers is going to be rational as well, that it's going to be an integer divided by an integer when I multiply them. So that means I'm going to multiply by substitution XA over YA by XB times over YB, and that comes out to XA times XB over YA times YB by the way we multiply fractions. What I've done here is just substitution and arithmetic. So I've kind of combined steps here, and you can do that, but try not to do too many steps in one so that it's clear where things are coming from. This is not a series of very over-the-top statements, so we can combine them into one. So now I see that A times B is a ratio of two numbers, but I have to make the argument that those two numbers that are being divided, XA, XB, and YA, YB, that those are integers. Well, if XA is an integer and XB is an integer, that means XA times XB is an integer. How do we know that? This is by closure. I'll just say by closure. And also YA times YB is a product of integers, therefore it's an integer by closure. And there's one more stipulation for this being a rational number. We can use a substitution here. Let's call this just X, and let's call this just Y. So X will be XA times XB since it's an integer. Y will be YA times YB. Now I just have to make sure that the denominator is not zero. But we already said that YA and YB are not zero. Therefore, YA times YB can't be zero. So YA times YB is not zero. So since YA is not equal to zero, YB is not equal to zero, YA times YB is not equal to zero, right? The only way for two numbers to multiply and give me zero is for both of them to be zero. And well, wait a minute. Now we can write our really final step here, the one that I like to always do, just to put a solid closure on this. So I see that A times B is the product, or is the ratio of X and Y. And because it's the ratio of two integers where the denominator is not zero, this is a rational number by definition. And that's it. We've just proven our original statement. We have proven that if A times B is irrational, then A is irrational or B is irrational. Now, it may not seem very gratifying that we proved that because we actually set out to prove it, but then we proved the contrapositive. However, again, the contrapositive is logically equivalent. So proving the contrapositive is the same thing as proving the original statement. And once the most challenging part about doing contrapositive is rewriting those statements. And then when you're doing the proof, then you're still doing a direct proof, but it's the direct proof after you've taken the contrapositive. So we'll go ahead and stop there.